You standing in your kitchen with bare feet on the floor, waiting for the kettle. There's 1.5 meters between the top of your head and the tiles under your toes. And your head has, measurably, been alive slightly longer than your feet have. Not a figure of speech, a number in seconds. Most people file this under black holes in spaceships, something a long way off happening to somebody else. That difference already shows up over 2 steps of a staircase. The strange part isn't that it's true. It's what that tiny difference actually is. Nearly everybody has the direction backwards. Gravity slows time down. Down by the floor, you're closer to all that planet, so time runs slower there. Higher up, it runs faster. Your feet are the slow ones. Your head is the fast one. Einstein predicted that in 1907. He thought the difference was too small to measure on Earth. For 50 years, nobody had a clock good enough to check. Then 2 physicists at Harvard used light instead of a clock. Light has a frequency, how many times the wave goes up and down every second. That's a clock already ticking. Some atoms give off light of one specific frequency, the same number of ticks per second. In 1959, Robert Pound and Glenn Rebka put a speck of radioactive iron at the bottom of Harvard's 22-meter tower and pointed that light straight up. At the top, a detector made of the same iron would only catch the light if the frequency still matched. It didn't. Climbing away from Earth, the light arrived lower in frequency than it left. Fewer ticks per second at the top means the bottom was running slow. Sent downwards, the light arrived higher. The apparatus was a tower in a physics building, and the experiment was shining a light up the stairs. They matched Einstein's predicted shift to about 10%. 5 years later, Pound and Snyder tightened it to 1. The prediction the man himself thought was untestable on this planet was confirmed in a university stairwell. If you like this kind of video, an ordinary fact about your own body, or a piece of physics somebody actually went out and measured, like and subscribe. The tower was the easy version. First, somebody tried it on an aeroplane. Then the distances started shrinking. In 1971, Joseph Haffel and Richard Keating flew 4 atomic clocks around the world on ordinary airline flights, east, then west, and compared them against the clocks they'd left in Washington. They came back disagreeing by hundreds of billionths of a second. First time anybody caught this on an aeroplane. It's a messy result, though. A plane is high up, and it's also moving fast, and moving clocks run slow, which pulls the other way. 2 effects, 1 number. For height on its own, you want the experiments with a ruler. In 2010, Cho and Wineland's group at the National Institute of Standards and Technology in Boulder built 2 clocks, each accurate to a second in 3.7 billion years, and linked them so they could compare the ticks. Then they raised one of them by 33 centimeters. The raised one ran faster than the one still on the bench. They published it in Science. 33 centimeters. 2 steps of a staircase, and the clock at the top was already ahead. Then, in February 2022, Jun Yi's group at JILA in Colorado published a result in Nature. They stopped needing 2 clocks. The atoms themselves were the clock. They cooled 100,000 strontium atoms into a cloud 1 millimeter tall, and compared the tick at the top of that cloud with the tick at the bottom. The top and the bottom of one speck of atoms disagree about what time it is, and the atoms on top age fastest. That's the Harvard Tower experiment run 22,000 times smaller. It's the current record, not the floor. Nobody thinks a millimeter is where this stops. So how big is it on you? The rate is fixed, and it's tiny. Go up a meter and your clock speeds up by 1 part in 10,000 million, which means nothing to anybody, so here it is in a life. Stand upright for 79 years and the top of your head finishes a few hundred billionths of a second ahead of your feet. Live a mile up in Denver and you gain 0.4 of a millisecond on somebody at sea level. And that's the generous version, because it assumes you stand up straight for 79 years. You spend a third of your life lying down, head and feet at the same height, gaining nothing. Nobody has ever felt any of this, and nobody will. If you've ever felt time speeding up as you got older, that's real, and it has nothing to do with your height. There's a video on this channel about it. Short version: it isn't your aging body running slow, it's novelty. Your memory records new things, and by 40, there are fewer of them. Too small to feel isn't the same as too small to matter. There are satellites over your head right now, 20,000 kilometers up, each carrying an atomic clock. Up there, the Earth's gravity is weaker, so those clocks gain 45 microseconds a day on ours. They're also moving, and moving clocks run slow, which costs 7 microseconds back. Net, 38 microseconds a day, fast. Your phone works out where you are by timing those signals. Light travels about 300 meters in a microsecond, so a clock that's even slightly fast looks like a satellite in the wrong place. 38 microseconds a day of clock error is more than 10 kilometers a day of position error, and the system falls outside its own accuracy spec within minutes. So they build the correction in. The clocks are tuned to the wrong rate on the ground before launch, so that up there they run right. Nobody's fixing them every morning. It's in the hardware. Right. Forget clocks for a minute. Why does anything fall? The ordinary answer is that gravity pulls it. There's a force. The Earth is on one end of it, the falling thing is on the other, and it drags one toward the other. Here's the other answer. Everywhere a human being has ever been, on the ground, up a mountain, in orbit, gravity is, to a very good approximation, just time running at different speeds at different heights. A ball on a shelf is going nowhere in space, and it's still traveling forward through time. The shelf is holding the ball up. That's the only reason it isn't falling. Let it go. Time runs slower nearer the ground, and the ball drifts toward the slow clocks. That drift is what falling is. Things fall toward where time runs slowest. You are not being tugged at. You're drifting downhill in the rate of time, and the tiles are what's stopping you. This is the part I find hardest to believe, and it's the part least in doubt. It's what Einstein's theory of gravity gives you for the weak kind, which is the only kind any of us has ever met. Go somewhere extreme, the edge of a black hole, and the full description gets much bigger than this. In a kitchen, it doesn't. Which is why that 33-centimeter measurement in Boulder is the one worth keeping. Two clocks, 2 steps of a staircase apart, disagreeing by a number with an enormous string of zeros in front of it. That disagreement isn't a side effect gravity produces while it's busy doing the real work. At the scale of a person in a kitchen, it's very close to being the whole thing. So, bare feet, tiles, kettle. Your head is a few hundred billionths of a second older than your feet over an entire life. Too small to feel, too small to matter, never once in doubt. People have measured the difference up a tower, on aeroplanes, across 1/3 of a meter, and inside a millimeter of atoms. And that same difference, time running at different speeds between the top of your head and the floor, is the reason you're pressed into those tiles at all. It's the smallest difference anybody has ever bothered to measure. You're standing on it.